Welcome everybody to this week's Chalmers Functional Programming Seminar. I see there's very many people already watching. That's great to see. Let's start right away with the introduction to this week's speaker. This week's speaker is Nadia Polikarpova. She's an assistant professor at the University of California in San Diego. And these days she mainly works on program synthesis. So I'm excited to hear what she's going to talk about. So please take it away, Nadia.
Thanks, Koen, for the introduction. Hi, everyone. My name is Nadia. And today I'm going to talk about some work that I've been doing recently with my student, Tristan Noth, and our wonderful collaborators from CMU, Jan Hoffman and Dee Wang. And this talk is about liquid resource types for verification and synthesis. Right, so really this talk is about analysis of programs' resource consumption. And how did I come to work on that? Because like Koen just said, I mainly work on program synthesis these days. So let me motivate this work with an example from program synthesis. Okay, so what is program synthesis? The goal here is to generate programs automatically from some high-level specification of their behavior, as well as some description of components or building blocks that the synthesizer can put together to make a program. And in my work, I'm in particular interested in the situation where the specification and the components are both described using types, especially some kind of expressive types. So in particular, maybe you're familiar with one program synthesizer that I built that is called Synquid. And Synquid takes as input something that's called liquid types to describe both the specification of the program and the components. So let's see an example of a program that Synquid can generate for us. So let's say we want to compress a list. What do I mean by that is just remove adjacent duplicates from a list. Let's say we have a list with some 2s and 3s in there. And so what we want to do is just remove, the adjacent 2s and the adjacent 3s, but, the 2 2s can stay in there as long as they are separated by this 3. Okay, so this is what we want to achieve. And if you're a functional programmer, that it would be pretty easy for you to think about how to do that, right? So if you have a list that is non-empty, it has a head and a tail, then you might want to recursively compress the tail first, and then compare the head of your list with the head of the compressed tail. And if they're the same, throw one of them away and you're done. So it's actually a really simple recursive function that can achieve this goal. Okay, so but let's say we are too lazy to write this function for whatever reason, and we want to ask Synquid to generate it for us. How can we write a specification for this function that Synquid can use? Well, like I said, the specifications for Synquid are types. So what if we start with a simple sort of Haskell style type for compress? Well, that type could be, it takes a list of A's and produces a list of A's. Well, that type is not particularly descriptive. If we ask Synquid to generate something of this type, it will probably just generate a program that always returns an empty list. So to really explain to the synthesizer what we want, we need to use these advanced features of liquid types, right? That can add more descriptive specification to this type. And I'm not going to go into detail right now about how to describe this, but it turns out that with liquid types, you can define a separate data type that I will call CList for compressed list, which basically enforces that there are no adjacent duplicates in this list. And additionally, we can refine this return type with a little logical predicates that basically says that the set of elements in our return list should be the same as the set of elements in our input list. So now we can give this type as the specification to Synquid, along with some components, like, for example, we can give it definitely the definition of list and compressed list, and also perhaps the equality operator so that it can compare the elements of the list. By the way, in this talk, we will just assume that any elements of any type A are comparable just for simplicity. And then Synquit can generate some code for us. So let me give you a little demo of how that will work. So what I'm showing you now is the web demo of Synquit. I will give you a link to that later at the end of the talk. I will not give you a link. Please don't go to the demo and try it all together right now, because it is not prepared to handle too many people at the same time. Let me also perhaps increase the font even a little bit more, just so that you can see what's going on here. So as you can see, I have, as you can hopefully see, I have given Synquit the specification for compress that we have just seen in the slide. So the types list and CList are defined up there in the source code. And I'm also defining the equality operator, right? So I'm saying that it takes an X and Y of type A, and it returns a Boolean that is exactly equal to whether these two inputs are equal, right? And instead of the body of compressed, I put this double question mark, which signals to Synquit that this is the function that it needs to generate. So now I can press this run button, and with any luck, soon we will get a recursive implementation of this function in this simple function language that Synquit is using, which is sort of like Haskell inspired, but not exactly that. But if you're familiar with Haskell or ML, you should be able to read this program pretty well. But so I also copied this program onto the slide. So let me switch back to the slide. So here's the same program. I renamed the variables a little bit so that it's easier to read. So now I will give you maybe 10-20 seconds to stare at this program and think to yourself whether you're satisfied with what Synquit has generated for us. Is this program correct? Is this how you would write it? Okay, as some of you perhaps have figured out, this program is functionally correct. It satisfies the specification that we gave to Synquit. But there is one problem with this program. It is extremely inefficient. In particular, this program runs in exponential time. This is, really surprising. So the reason it does is because it actually makes a recursive call of compress on the tail twice on the same path, right? And when you do that, it turns out that your program becomes exponential. So the second call to compress, if you wrote this program, you would probably just replace that with, cons of z to z's, right? Because this is exactly, this term is exactly equivalent to making the second recursive call, but of course does not. But of course, it executes much faster. So why did Synquit do that? Is it because it hates me? No, it's really because it doesn't know any better, right? So Synquit can reason about this sort of intricate functional properties that we can encode using liquid types, but it cannot reason at all about program resource consumption, about their efficiency, right? And moreover, Synquit tends to pick shorter programs over longer programs, right? And so compress-wise was just a little bit shorter than the equivalent program, equivalent term cons CZs. So it just picked that one. And it turned out to be not a very good choice, right? So something that we learned from this example is that if we want to generate efficient code, we have to teach our synthesizers to reason about program efficiency, to reason about program resource consumption. Right, so sort of to sum up, what we have now is a synthesizer where we can tell it to compress a list, and it gives us a shorter program that doesn't have very good performance. And what we want instead is to be able to tell it, okay, and also make it quick, right? And it would also, so in particular, tell it, okay, can you please do this in linear time? And then it would generate a program that might be slightly longer, but has, linear complexity. So this is our goal. This is what motivated me to start working on this project. Okay, so in particular, to achieve this goal, this work proposes a modification to the liquid type system that we call liquid resource types, which basically allows you to describe and to reason about both the functional properties of a program and its resource consumption, right? And this is what this talk will mainly be about. And we implemented this type system in a synthesizer that we call resin. That is essentially, it's similar to SyncWit, except it also takes resource bounds of programs as specification, and it can generate programs with provable guarantees, not only about their functional properties, but also about their resource consumption. All right, so the rest of the talk will be split into sort of these four little parts. So in the beginning, I'll tell you about how did we put this liquid types together with resource bounds to be able to describe both functional properties and resource consumption of recursive programs. I will then give you a little bit more detail about how we actually type check programs against these liquid resource types. And towards the end, I'll tell you about two more advanced features of this type system that I think are really nice because they're kind of simple, but they also allow you to reason about more advanced properties of programs. So I'll tell you about how we can reason about nonlinear bounds and also value-dependent bounds. So, and by the way, these parts of this work were published last year at PLDI, and the extension to nonlinear bounds is conditionally accepted to ICFP, so hopefully will appear soon as well. If there are any questions on Slido for just the introduction, then I would answer them now. Okay, I see a question. For the duplicate compressed wise, can that also be left as a for compiler to optimize? This is a really good question, right? So because the example that I showed you with the compressed, sort of the difference between the efficient and the inefficient program was very small. It was just this one small term, right? And you can reasonably say, sure, this is something that the compiler should be able to optimize. But we also have examples in the paper, if you look up the PLDI paper, where the difference between the efficient and the inefficient program is much bigger. For example, there is an example where we are trying to compute an intersection between two sorted lists, right? And if you don't specify any resource bound, then it would do that in quadratic time, sort of by it would traverse the first list, and for each element of the first list, it would traverse the whole second list to figure out if the element is present there. And if you specify that you need to do it in linear time, it would do it sort of as a zipper, traversing both lists at the same time. Question from Matthias: can SyncWit take an already written liquid type annotated program and massage it to have better resource use? Oh, this is a really good question. So it cannot do it just yet. So we haven't worked on sort of program optimization yet, right? But this is definitely something that we want to address in future work, because if you already have an implementation, first of all, you might want to infer the functional specification from that so that you don't have to write one yourself. And you could, sort of take hints from that to make the synthesis more efficient. This is certainly really an interesting topic, but we haven't explored it yet. Is the expression of the silliest type lower complexity than writing such a program? Oh, so right. I mean, I get this question a lot, Is writing specs actually easier than writing programs? It depends. I probably don't want to get into the discussion right now because it's sort of a common question for program synthesis, not really specific for this, but we can take it offline later. Okay, I think I'll move on at this point. Okay, so let me move on to the first part of the talk. How do we put liquid types and resource bounds together? Okay, so first, really simple introduction to what these liquid types actually are. Liquid types are types refined with very simple, decidable logical predicates, right? So for example, if we have a type int, we can refine it with a predicate like so to describe the type of natural numbers, right? So this type here says it's a type of value such that this value is greater or equal to 0, right? And this logical predicate here is called the refinement, right? So this is a type of natural numbers. And you might think, okay, so what's the big deal? You know, I can say that something is greater than 0, big deal, right? But actually, the cool thing is that refinements combined with other features of the type system in a really nice way. In particular, they combine really nicely with polymorphic data types, right? So if you put this natural number type as a parameter to a list type constructor, all of a sudden, what you're describing is a list of natural numbers, right? So it gives you this way to describe a universal property of list elements without using any quantification, right? By just using this very simple predicate. And because of that, liquid types allow you to verify non-trivial properties of programs fully automatically using an SMT solver, right? Because you're only using predicates that are from logics that are efficiently decidable by SMT solvers. Okay, so what's our idea? Well, if you want to describe not only functional properties, but also resource usage of programs, our main idea sort of in this work is, well, let's augment these types in addition to this logical refinement with a numeric term that describes the amount of potential stored in the value of the type, right? And the potential is sort of this, you can think of it as how much resource is stored in this value, right? And this resource can be then used to pay sort of for computation, right? You can think about it this way. So for example, this type that I wrote here, describes a natural number with a single unit of potential, right? And the cool thing about that is, again, because we put the resource annotation inside the type, it again composes really nicely with other features of the type system. For example, we can put this type inside a list constructor, and what we obtain is a list of natural numbers where each element has a unit of potential. So the list as a whole now has the amount of potential equal to its length, right? So we were able to distribute this potential sort of uniformly throughout the data structure without really talking about its size in any way, right? So we're still using a very simple annotation, which is a constant 1, to describe this uniform distribution of potential inside the data structure. Okay, so we're going to use these resource annotated types to describe two things. First, we want to describe the cost model of the components, meaning how much does it cost to invoke each one of our components. And we want to describe how much resources we want the program to consume. So how would we do that for our compress example? So first of all, in the compress example, let's say we want to tell it that an equality comparison on elements actually costs something, right? So let's say we want to say that it costs 1 unit of potential. So this was sort of our type for equality. We're going to just make one small change to it. We're going to annotate the second argument with a single unit of potential to say that, well, to invoke this equality, you need to sort of pay, 1 unit of potential for that. Okay, so that was the cost model. Now for the resource bound, remember this was our type of compress, again, we're going to make one small change, and we're going to annotate the argument and say that now each element of this input list has a single unit of potential, right? And this intuitively expresses that, well, this program can only make, one operation per element of the list, right? So it has to run in linear time. Okay, so given these two enhanced specifications, let's see what resin is going to do if we give it this spec. Let me go here and I'll switch to my other tab. Wait a second. Switch to my resin tab. So in this tab, I just made the modifications that I just showed you. I annotated the equality and I annotated the input type of compress. And let's say what resin does if we run it on this specification. Otherwise, the specification is the same as we had before. And as you can see, exactly what we wanted happened here. There is no more second recursive call to compress. Instead, we have a cons as we expected, right? So resin generated a program that runs in linear time, just like we wanted. Okay, great. So, so this was just sort of a high-level overview, the demo, and I would move to the part where I actually tell you about how type checking works. But let me check at this point if there are any other Slido questions. Oh, so is resource annotation tracking one type of resource? So actually, this approach is very flexible because, like I said, you can annotate your components in any way you want to describe your cost model, right? So, for example, so if you want to track time, then you can annotate sort of operations that you expect to take some time. If you want to track memory, you can annotate, for example, the data type constructors with cost, and that would sort of correspond to tracking memory. So it's pretty flexible. What happens if a queue gets annotation of 1 for both x and y, not only y? Oh, then it would have cost 2, right? So basically, you can think of as a cost of an operation is sort of the total potential required by its arguments. Maybe I can answer just one more. How much work is it for the synthesizer to use the resource annotation? Actually, it's not. So if you look at the PLDI paper, we have some stats about how much longer it takes resin to synthesize programs than Synquit. So what we found is that, well, synthesis in general is kind of slow because it's a search in a huge space. So in fact, the only times where resin is significantly slower than Synquit is when the efficient program is very different and much larger, right, than the inefficient program. So really it just takes it more time to search for this program rather than do the type checking, right? So this type checking is a little bit extra work, but it's not too much. Okay, so maybe let me move on at this point because there's an infinite supply of questions which I cannot all answer. Okay, so let's move on to how the type checking of programs against these resource specifications actually work. And by the way, I wanted to note that from this point in the talk, I will never talk about synthesis ever again. And this is because the way type-driven synthesis works essentially is you just give it a type checker of an appropriate kind, and the synthesizer just sort of folds out automatically from that. Essentially, what synthesis does is some kind of backtracking, search in the space of programs using the type checker to prune the space. If you want to learn more about how this type-driven program synthesis works, you can watch one of my other talks, for example, my strange loop talk from 2018. But from now on, for the rest of the talk, I will just focus on how the type checker works, how we actually check the programs against these resource specifications. Okay. All right, let's dive in right into the example, and let's see how the exponential version of compress would be checked against this resource specification that we gave it, and see why it would be rejected by the type checker and hence not synthesized by the synthesizer. All right. So we're checking compress against this type where the input list has 1 unit of potential per element. And so from now on, I'm also omitting the functional specification just for simplicity, right? So like I said, Resin can reason about both resources and functional properties, but I just don't put it on the slide. So we are simply verifying the resource bound, but we are not anymore verifying that the resulting list is compressed. Okay, so this was the inefficient version that we generated that we want to check against this type. All right, so when we go inside the body of compress, right, that we want to check against the type list of A's, we get these variables in our context. As you can see, there's a context on the top right of the slide. In our context, we have compress itself because it is a recursive function. So we have it now available. And the argument of compress, which now has sort of some resources associated to it, right, that are now available for us to pay for whatever happens in the body of compress. So the main idea of our type checking is that we're going to go through the program, and our type checker is going to generate some constraints, some arithmetic constraints that will only have a solution if we can partition resources that we have available in the context to between all the terms in the program that require some potential to be type checked. Okay, so let's see how this works. So the very first top level term that we have in this program is a pattern match. And a pattern match has sort of two things for us to execute, right? So we first have to execute the match scrutiny, and then depending on what it is, we have to execute one of the branches, right? So we cannot really type check these two parts of the program in the same context, because that would be duplicating resources, right? So in fact, the resin type system, the liquid resource type system is an affine type system, in the sense that whenever we have a term like this, like a pattern match, or any other term where there are two subterms to be executed along the same path, we have to split this context into two, basically splitting all the resources that are available, and then type check one part of the program in one context and the other part in the other context, right? So here we split it into a blue and a green context, and the blue one will be used to type check the scrutiny, and the green one will be used to type check the branches. And essentially, we have to apportion the potential that we have stored inside X's between those two contexts, right? So in this case, it's actually kind of trivial, because the green part of the program doesn't even mention X's. So we can actually put all the potential that's inside X's inside the blue context that goes to the scrutiny. But we will see a more interesting example of that, of this context split later. Okay, so since we put all the potential into the scrutiny, then we would infer the type for the scrutiny, that is a list with a unit of potential in every element. Because this is the type of our scrutiny, when we are destructing it, just by matching the type of the cons constructor against the type of X's, what we get is that the head Y is now of type A with potential 1, and the tail Y's is of type list of A's with potential 1. So now this will be the context in which we check the cons branch of this match, right? As you can see now, we have this head with a single unit of potential that kind of got freed up for us to pay for some operation. At this point, we again have a pattern match. But this one, so we again have to split the context. But this one is more interesting because we have a variable y's that appears in both parts of this pattern match. So we can't just simply decide where all of the potential goes. So we introduce these symbolic annotations, and we say some amount of potential P goes to the scrutiny, and some amount of potential Q goes to the branches. All right. So this will be sort of the type of Y's in each part of this program. And this context split actually generates this arithmetic constraint for us that says that the total potential in Y's has to add up to 1, right? Because this was what was in our original context, right? So we need to make sure that P plus Q is equal 1, in other words. All right, so now when we concentrate on the scrutiny of this match, this is a function application, right? So like in any function application, we need to make sure that the type of the actual argument is a subtype of the formal, right? And here what it means is that we have enough resources inside Y's to actually call compress. And as you can see from the context, the type of compress requires it to have 1 unit of potential per element, right? So now we need to know that P is greater or equal than 1, in other words. And finally, when we start checking the branch, the same thing happens because we're calling compress again. We need to know that Q is also greater or equal than 1. So we get the system of constraints, and if you look at them for just a little bit, you will realize those constraints are unsatisfiable. So you cannot have 2 numbers that are greater or equal than 1 add up to 1, right? And the SMT solver can tell you really easily that this system is unsatisfiable, so this program does not type check. So what if, so this is a type error. So what if we were to type check the linear version of compress against this type? So when we get to this same inner pattern match, we can now actually, so because we don't have Y's appearing in both sides anymore, we can send all the potential that is stored inside the Y's variable towards the only occurrence of Y's, which will make it so it's sufficient co-compress on those Y's. And then we send the potential that's stored in the head, the single unit of potential is stored in the head, to the comparison operator so that we can pay for the comparison, right? And now there's no potential used in any of the other parts of this program, so this program is well typed. So as you can see, what happened here, as we were destructing this list that has 1 unit of potential per element, we were sort of freeing up this single unit of potential at a time that is attached to the head of the list that we can then use to pay for the comparison, right? So this is how this type checking works. So I'm not going to bore you with the formal details of this type system. I'll show you a couple of typing rules just so that you get a taste for it. The PLJ paper has a whole bunch of them. So like I told you that one of the most important features of this type system is this context sharing or context splitting, right? Which makes this, gives this type system this affine flavor. So in particular, if we want to type check something like a pattern match, to do that, we need to split our context into 2, right? Where this premise essentially means that gamma 1 and gamma 2 have the same variables as gamma, except that their potentials add up to what they have in gamma. And then the match scrutiny is type checked in the first environment, and both of the branches are type checked in the second one. And another interesting rule that we used during this type checking was the subtyping rule. So the subtyping rule for types that are annotated with both refinements and potentials, this is a little bit simplified, but it goes this way. So in standard refinement types, liquid types, one of the premises of this rule is that the refinement of the left-hand side has to imply the refinement of the right-hand side under the assumptions that we extract from the context. We'll see some examples of those assumptions later in the talk. And so what we add to this is that the potential in the left-hand side also has to be greater or equal than the potential of the right-hand side. Again, under some assumptions in the context, and we'll see later where these assumptions would actually come in handy. Okay, let me see more questions on Slido. So Kuhn is reminding me of the top voted. Okay, the top voted question is a particular element of the list of type v int true 1 whose length is greater or equal than 2 is possible to reference twice, or each element is referenced at most once. So this is a very good question. So it's really our type system, like I said, is affine, and you have to split the context whenever you're type checking sub expressions, but it doesn't mean that you can only reference a variable in one of those contexts. Like I said, when you split the context, like I just showed you that this rule, right? When you split the context, both of those contexts, gamma 1 and gamma 2, have all the same variables, except that their potential gets split up, right? So you might be referencing a variable many, many times, as long as the context in which you're referencing it doesn't actually require it to have any potential. But once you try to use it as an argument to something that requires potential, then you would need to allocate some actual potential to it. And then there will be the number of times you can limit it in this way would be limited. Okay. So for the question is, how do resource bounds on liquid types compare to linear type systems? Yeah, this is a very good question. So this whole this work is very much related to all kinds of linear types and fancy linear types for Haskell and other functional programming. So there's linear Haskell. There is work on Granule, right, with bounded model types and such. It's very much related to that. So we think that one difference is that we come from the point of view of resource analysis, and we use this automatic amortized resource analysis and this notion of potential, which actually comes from Jan Hoffman's work on resource-aware ML. And it is because of that, it can allow you to analyze sort of more interesting resource bounds because it has this amortized resource analysis flavor to it. And so the other, I guess, difference is that it combines really nicely with liquid types in particular. So we designed this type system very carefully with automatic verification in mind. So we want to make sure that all of these annotations are checkable completely automatically by an SMT solver. And this is why, this is what the design is driven by. But it's definitely related to all kinds of linear types work. Is it possible to split potential between two uses? For example, in divide and conquer algorithm. Yeah, exactly. So it is possible to split it. So as you can see here, so the constraints that we generate for compress here, right, they allow you to split the potential between two uses of y's. It's just that in this particular case, those two uses were too expensive, right? But it's definitely possible to split it in such a way that it's not too expensive. And you can actually type check it, right? So, and we'll see an example later if I get to it with all these questions. Can type checking identify some bad resource annotations? Well, I mean, it will if you write the program yourself and then you give it a resource annotation that doesn't hold. It will just give you a type error. So then if it gives you a type error, the error is either in your program or in your resource annotation. If I understand the program, if I understand the question correctly. Can the resource checker handle amortized costs? For example, split P and Q based on probabilities. Oh, interesting. So we don't handle probabilities, but it is amortized analysis, right? So you can basically store this potential in the data structure. Yeah, so it's all built on amortized resource analysis, the way it's done in resource-aware ML, except a bit more expressive with liquid types. Okay, so maybe let me move on at this point and I'll answer more questions at the end. All right, so because I really want to get to these more fancy features I wanted to show you. Okay, so let me talk about nonlinear bounds a little bit. So we're going to switch gears to a different running example in this part of the talk. And our running example is going to be insertion sort. So in case you might have forgotten how insertion sort works, so it takes as input a list that it needs to sort. And then if this list is non-empty, it has a head and a tail, then it would call sort recursively on the tail. And once it gets the sorted tail back, it would traverse the tail once again to insert the head in an appropriate position inside its tail, right? And this is, and now the list is sorted. Let's say we are interested in the resource consumption of insertion sort, right? How many steps does it take? So in particular, one way to phrase this question more precisely is how many comparisons between elements does insertion sort make? Okay, so let's see how we can implement this sort in this functional language that we have. We can write sort pretty straightforwardly as a recursive function this way. And then now we are relying on this auxiliary function insert that inserts an element into a sorted list that we can also implement pretty straightforwardly. So now we want to give some, so first of all, we need a cost model, right? So we give the following type annotation to our less than equal operator. And we say that it's going to have a cost of 1. And now our goal is to give resource annotated types to both insert and sort to basically capture their resource usage. Well, for insert is pretty easy. Insert is linear in the list. So we can simply, as before, give one unit of potential to every list element. And insert will verify against this bound, no problem. But what should we do with sort? Sort is not linear, right? So we all know that sort is quadratic. And so this doesn't really fit with our with the way of annotating programs that I showed you so far, where we could just stick these constant annotations inside the list elements, right? Because that only allows you to basically assign linear amount of potential to a data structure. In particular, it only allows you to distribute potential uniformly throughout the data structure. But this is not what we want for sort, because in particular, sort is traversing the later elements of the list more often than the earlier elements. So we would actually like some mechanism to assign more potential to the tail of the list than to the head of the list, okay? And then we hopefully will be able to verify sort. So how do we do that? We cannot do that with the mechanism that I showed you so far, but there's this very simple idea that we had that we call inductive potentials. So here I'm just showing you the regular definition of list, polymorphic list data type. So the idea is we can annotate the data type definition itself with potential annotations to specify how potential is distributed inside the data type. So in this case, we can define a special data type that we're going to call QList. So far, I only changed the name of the data type, didn't really change anything else yet. But what I'm going to do is, if you look at the type of the constructor, right, type of the tail is polymorphic in the element type, right? So I don't actually have to have A there. I can put wherever I want there. And what I want there is A with some extra potential. So what this means is that every element in the tail will have at least one extra unit of potential compared to what the type A itself has, right? So A is a type variable, can be replaced with some type that has potential. And then if we put extra potential on top of A, and this will sort of add up to the potential that A already has. So is this really what we want? Does this describe quadratic potential that we need for insert? Well, yeah, I mean, if you have a list like this of type Q list, let's say with elements of type int with potential 1, this means that your head will have a potential 1. The next element will have 1 more, meaning 2. The next element 1 more. The next element 1 more. So the total amount of potential in this list is actually will add up to n times n plus 1 over 2, where n is the length of the list. So it's going to be quadratic potential, and it's going to be exactly what insertion sort actually needs. So let me quickly show you how we can actually now type check insertion sort against this bound, giving its argument the type Q list of A's with potential 1. So here in the context for the body, we have, well, first of all, we need to have insert because this is an auxiliary function. We have sort itself because it's recursive, but also let me note that in Synquit and in Resin, we use polymorphic recursion. So the type of the elements in the sort can be some other type, not necessarily A. And of course, we have X's that is itself a Q list with A1. So the most interesting thing happens when we match on X's that has this weird Q list type, right? So recall that the type of the const constructor is this, right? So if you, so in this case, the type T is actually A with potential 1. So if you, so because of that, the head is going to have the type A with potential 1, but the tail is actually going to have the type Q list of A's with potential 2, because we added the one that we had on X's with the one that came from the type of const, right? So you see here's exactly where the magic happened, right? So in the context for the const branch, now have this this tail floating around, which has one more potential in each element than the original list had. So because of that, because this wise has more potential, we can definitely call sort on it. But because sort is polymorphic, we will instantiate sort with the type variable of sort with A with potential 1 instead of just A. So sort now has the type Q list of A's with 2 to a list of A's with 1. And hence the result of calling sort will be of type list of A's with 1. And this is enough potential to call insert, right? Otherwise, if we didn't get this extra potential on the tail, we wouldn't have enough potential to call insert. And so now both sort and insert type check, okay? At this point, let me just quickly go through the last part of the talk, which is very related to this one, and then I'll take the remaining questions. So we're sticking with our insertion sort example. So what we were able to prove so far is that insert executes in linear time, whereas sort executes in quadratic time. But this is a coarse-grained bound for insertion sort. We actually know something more about insertion sort. In particular, we know that insert, it short circuits, it never traverses, so it almost never traverses the whole list, right? In fact, it only makes a comparison per element of the list that is less than X, right? Because once it finds the appropriate place where to insert X, it does not go any further and make any more comparisons. And insertion sort, we can actually say that it makes one comparison for every pair of element in the list that is decreasing, right? This is an important property of insertion sort because it basically means that if the list is already sorted, insertion sort is going to be very fast, right? And otherwise, you know, so it gets faster the more sorted the list is. right? So how can we specify these more precise bounds? So in fact, with our potential annotations, so far all the potential annotations that I showed you were just constants, but this doesn't have to be the case. Just like refinements can use, logical refinements can use program variables, and so do the potentials. So for example, we can replace this one here with this new variable, and this will denote a natural number whose potential is equal to its value. Right, so this is what we call value-dependent potentials, and so we can use this mechanism to specify this more finer-grained bound on both insert and insertion sort. So this is our old bound for insert, but in fact we can replace that one here in the potential annotation with a term, with a conditional term, right? So this new bound basically says that we only assign potential to those elements in the list that are less than X, right? And now we actually need to assign one more potential to X, in fact, because we are making one more comparison with that, right? So we still need to make one more comparison when we discover that we are in the right place, and then we stop. Okay, so and this will all sort of check out as a type check as before. So here, the important thing that happens is that when we are type checking the const branch and the alternative branch of the conditional here, we somehow have to pay for this whole recursive call to insert, and we can do that because in this branch, liquid types allow us to assume that y is less than x. And because of that, the potential that we have to y that's conditional now becomes 1, right? Because we can prove that in this case it's 1 and not 0, because we have this path constraint that y is less than x in this case, so we can still pay for our recursive call. And we can do a similar thing for sort, right? Remember that for sort, we have defined this type QList, but we can change that type to something that I call ISList, as an insertion sort list, where the type of the const constructor is refined in this very specific way that only gives more potential to those elements of the tail that are less than the head, right? And then in this case, we can verify sort just fine. The problem with this data type here is that it's very specific to insertion sort, right? It's not very reusable. So to give the type system a bit more flexibility, we introduced this one last feature that we call abstract potentials. So here the idea is that we allow you to parameterize the data type by a potential function that then you can use to specify potentials inside its definition. So we can define actually a general list data type that is parameterized by this Q function that is like a logic level binary function that you can then use inside the type of cons to give more potential to each element of the list, depending on, but the amount of potential is dictated by the Q function and doesn't have to be always the same, right? So, and now finally, with this generic, list with abstract potentials, we can specify and verify these fine-grained bounds for both insert and insertion sort without introducing any specific data types for each one of them, just using this one generic list data type that is parameterized by the potential function, and both of them will verify just fine. And this was essentially my talk. And at this point, I am happy to answer the rest of your questions. By the way, if you ever want to play with these tools, they're all available through web demos that are very easy to find from my webpage. So if you just Google me, and you'll see the links there. All right, let's see the questions. How would you ascribe the potential that map requires? Can you say that map fx requires the length x's potential for f? Well, for f, right? I would say that map itself, so it depends on I think what you're asking is, how would you say that F actually requires some potential? Because I don't think F requires length of X's potential, right? F will act on each element of X's at a time, right? So F might require some potential, but it would be strange if it is proportional to the length of X's, right? Because it acts on one element at a time. So I think, in fact, this system deals very gracefully with higher order functions, because if you just look at the regular type of map, right, without any extra annotations, because it's a polymorphic type, and because every type variable can be instantiated with a type that has potential, right, this type already tells us a lot. It basically tells us that, for example, that we cannot invoke the F function more than once on every element of the list, right? It wouldn't allow us to implement the map that way, because we know that F wants to consume all the potential that's stored in type A, and the list is full of A's, right? And so every time you apply F to one A, it will consume as much potential, and then that's why you can only apply it once to every element, which I think is actually kind of neat. But if you want to apply it multiple times, our type system also has this thing called multiplicities that you can attach to type variables. So for example, you can write a type of map that applies F to every element twice, right? But then you have to modify your list type to say the list is not a list of A's, but a list of 2 times A's. And then you can apply F. How does the programmer know to assign one potential to equals instead of one potential to other operations? Oh, this is a very good question. This is up to the programmer. This is how you define your cost model, right? So essentially, this is what makes this type system flexible, that the programmer can decide what they want to count, right? I just decided, oh, I want to count equalities. I could also say, I want to count recursive calls, right? Or I want to count the number of applications of a cons constructor, which would sort of correspond to the memory consumption in some way. So this is really up to the programmer. How error messages are generated from the output of the SMT solver. So good question. I mean, we are not really relying on, so when type checking fails, we just know that we tried to type check a certain part of the program, certain sub-expression, and the constraints became undecidable at this point. So we can just report that, this is undecidable, right? And show the kind of bound that we were trying to check. So we are not really relying on the counterexample from the SMT solver or anything like that. So in that sense, it's, I don't think that's very challenging here. The quadratic resource operation seems fragile because it is not in big O. Can we be more general? So right, so the specific, the Q list that I showed you, let me see. The Q list type that I first defined for sort is very specific. What was that? Right, so this one is very specific to this particular function, right? It only adds one more unit of potential to every element of the tail, which is, this is not very general, I agree. But once we parameterize the list with, so once we define this more generic list that I showed you here, you can parameterize it with any function you want. So you still cannot say, okay, any big O would do for me. So we don't support that yet. You have to, for each function, you have to specify a precise bound. But I mean, so Resin allows you to waste resources. So you can specify a bound that is not tight. But you have to specify your coefficients. But you don't have to define a new type once you have this type with abstract potentials, right? This looks very similar to what Idris 2 does for program search in the interactive environment using linear dependent types. Have you looked into possible? Yeah, so I'm aware that both I think Agda and Idris do a lot of type-driven program search that is similar to this. So it's a good question. I don't know the specifics of the differences with Idris, as I'm not intimately familiar with it. Yeah, so I guess because of that, I can't really comment. So I'll have to look into the details. I think perhaps the important connection here, which I don't think Idris property that Idris has, is that we really make sure that everything is decidable, efficiently decidable with SMT solvers and things like that. So so because of that, our type system might have restrictions that Idris might not have, because we want to keep everything efficiently decidable. Do you not need potential and arrows? Maybe just encode it as the outermost result type. This is a very good question, right? So we, in fact, the type system, I didn't show it in the slides. The type system does allow you to have potential and arrows. That's fine. We didn't need that in these examples. So in fact, so the potential and arrows doesn't, it's essentially not, I mean, it's not different from potential on any base type. So one interesting thing that does arise about arrows is that we also have linear arrow types, meaning functions that you can only apply a finite number of times. And that's important because otherwise you cannot really do partial applications. You have to be careful if there is potential on, let's say, the first argument of a function, which has multiple arguments, and then you partially apply it to the first argument, it sort of captures this potential inside the closure. And then if you're allowed to use this closure as many times as you want, you will be duplicating potential. So in fact, our type system specifically says, if you are, basically, if your abstraction is capturing potential in the environment, then you get a linear function type as opposed to like a regular nonlinear function type, which can apply as many times as you want. So I think that's an interesting part of the type system. The split rule seems to force every element to choose the same side of the split. What if there is a list element dependent split condition? So, right. I didn't want to do that. What I wanted to do was go to the split rule, which is, let me see. God. Okay. So you mean, okay, maybe we can go to like here. Right, so this is, I think, one of those parts of the type system where we sacrifice maybe some of the expressivity for efficiency of type checking. Right, so indeed, when you are sharing a list or any data type between two environments, you have to, basically every list element on the left gets a P and every other one gets a Q. And that's, that's just how the type system works. P and Q can be dependent though, right? So like, remember I told you at the very last part of the talk, all our potential annotations are in fact allowed to be dependent. So P here could be something like, if this element is greater than 5, then 1 else 0, and Q could be the opposite, right? If its element is greater than 5, then 0 else 1, right? And then it can depend on the value of the list element in that way, even though it has to be the same term for each element. I lost my slide. Okay.
Nadia?
Yeah.
I think it's time to wrap up now.
Okay.
So thank you so much for this great presentation. A lot of people have already applauded in the YouTube chat, but I will also applaud.
Thanks for great questions.
Yeah,
There
so
seems to be an
you will get a
infinite
log
source
of
of them.
you will get a log of these questions, and then you can look at those questions at your own leisure. So thanks to our listeners to come and watch this talk. I welcome all of you back next week when we have Kathleen Fisher talking. So see you all next week.
Right.
Bye.
Thanks, everyone. Thanks, Glenn. Bye.